8 statistical anomalies that make our planet an impossible outlier. What if I told you that the ground beneath your feet, the air filling your lungs, and the very fact that you are reading these words right now represents a statistical impossibility? Not a poetic exaggeration, not a philosophical musing, but a cold, hard conclusion drawn from astrophysical data. In 2025, a landmark paper published in the Proceedings of the National Academy of Sciences re-examined the massive dataset collected by NASA's Kepler Space Telescope using advanced statistical methods. And the results stunned the scientific community. Several exoplanet candidates previously believed to harbor Earth-like conditions turned out to be statistically unreliable detections. Kepler 186f, once celebrated as humanity's best hope for finding a twin Earth, was reassessed with a false positive probability as high as 20%. As of today, astronomers have confirmed more than 5,700 exoplanets orbiting stars other than our Sun, with over 10,000 additional candidates awaiting verification. Yet among all of them, not a single one has been confirmed to match Earth's precise combination of conditions. Not one. The reason is unsettling in its simplicity. Earth is not an average planet. It is not a typical rocky world sitting comfortably within the expected distribution of planetary characteristics. Earth is the opposite of average. It is an outlier, a data point that statistically should not exist within the dataset of known planets. A freak convergence of improbable conditions stacked upon improbable conditions. There are exactly 8 anomalies that make Earth what it is, 8 factors that, if any single one had been even slightly different, would have prevented complex life from ever emerging on this world. These are the Moon's absurd size relative to its host planet, the perpetual churning of Earth's interior, the precision of its magnetic shield, the placement of Jupiter in just the right orbital configuration, the quantity of water being neither too much nor too little, the atmosphere having been rewritten twice through catastrophic events that somehow left conditions perfect for complex life, the position of our solar system within the Milky Way galaxy, and the sheer temporal coincidence that intelligent life arose during the narrow window when observation of the universe is even possible. Each of these represents an independent low-probability event. And the fact that all 8 converge on a single planet challenges our understanding of how common or rare habitable worlds truly are in the cosmos. The Moon hanging in our night sky is so familiar that most people never stop to consider how profoundly weird it is from a cosmic perspective. Let us talk about size. The Moon's mass is roughly 1/81st that of Earth, a ratio of approximately 1.2%. That number might sound small until you compare it with every other moon-planet relationship in our solar system. Jupiter's largest moon, Ganymede, is bigger than the planet Mercury, an enormous celestial body by any standard, yet its mass relative to Jupiter is less than 1/10,000th. Saturn's Titan, another giant moon with a thick atmosphere and hydrocarbon lakes, is similarly dwarfed by its parent planet in terms of mass ratio. Survey the entire solar system, and you will find no other rocky planet with a satellite this proportionally large. Mercury and Venus have no moons at all. Mars possesses 2 tiny, irregularly shaped rocks called Phobos and Deimos, each only about 10 to 15 kilometers across, almost certainly captured asteroids rather than formed companions. The only comparable mass ratio belongs to Pluto and its moon Charon, where Charon is about 12% of Pluto's mass, making them almost a binary system. But Pluto is a dwarf planet, fundamentally different in nature and formation history from the major planets. For a full-sized rocky planet to possess such a disproportionately massive satellite is a phenomenon unique to Earth and our solar system. The question of how this giant moon came to exist has occupied planetary scientists for decades, and the currently accepted answer is as violent as it is precise. Approximately 4.5 billion years ago, when Earth was still in its infancy, barely solidified from the disk of gas and dust surrounding the young sun, a Mars-sized protoplanet slammed into it. This impactor has been named Theia, after the Greek Titaness, who was the mother of the moon goddess Selene. The collision was beyond anything in human experience, releasing energy equivalent to billions of nuclear arsenals detonating simultaneously. liquefying both bodies and ejecting a vast cloud of molten debris into orbit around the shattered proto-Earth. Over time, this ring of superheated material coalesced under its own gravity to form the Moon. In January 2026, new evidence supporting this giant impact hypothesis was reported when researchers found that the isotopic composition of 3.7 billion-year-old terrestrial rocks matched Apollo lunar samples with remarkable precision, strongly suggesting both bodies formed from the same well-mixed pool of material. Even more intriguing, a 2026 study proposed that the Moon may not have formed from a single giant impact, but rather from 3 or more successive large-scale collisions, which would more naturally explain why Earth and the Moon share such strikingly similar compositions. Regardless of whether it was one catastrophic blow or several, the physics demanded extraordinary precision. The impact had to occur at just the right angle, neither too head-on nor too glancing. It had to happen at just the right velocity, fast enough to eject material into orbit, but not so fast that the debris escaped Earth's gravitational pull entirely. The impactor had to be just the right size, large enough to produce a substantial Moon, but not so large as to destroy Earth completely. Had any of these parameters deviated even modestly, the debris would have either dispersed into space or fallen back to Earth's surface, and no Moon would have formed. The benefits this accidentally created Moon provides to Earth are almost incalculable, but the most critical is axial stabilization. Earth's rotational axis, the imaginary line around which it spins like a top, is currently tilted at approximately 23.4 degrees relative to its orbital plane around the Sun. This tilt is what gives us seasons, the predictable cycle of spring, summer, autumn, and winter that governs everything from agriculture to animal migration patterns. The Moon's gravitational influence acts as a stabilizer for this tilt, keeping its oscillation within a narrow band of plus or minus 1.3 degrees over tens of thousands of years. Without the Moon, the situation would be radically different. A classic 1993 simulation published in Nature demonstrated that a moonless Earth could experience axial variations ranging from 0 degrees, meaning no tilt at all and therefore no seasons, to as much as 85 degrees, which would mean Earth spinning nearly on its side like Uranus. At 85 degrees of tilt, the poles would periodically face the Sun directly, experiencing months of continuous scorching heat, while the equator would plunge into darkness and extreme cold. More recent studies have suggested that even without the Moon, Earth's axial variation might be somewhat more contained, perhaps oscillating between 20 and 25 degrees. But even this more optimistic estimate represents wild instability compared to the current 1.3 degree wobble. In a world where seasons shift dramatically over tens of thousands of years, where tropical regions periodically freeze and polar regions periodically bake, the stable long-term climate conditions necessary for complex ecosystems to evolve would simply not exist. Evolution requires consistency over enormous timescales, and the Moon provides that consistency. It was born from a cosmic accident of extraordinary precision, yet without that accident, Earth's climate would have swung chaotically through extremes that no complex biosphere could survive. A product of pure chance became an indispensable piece of infrastructure for life. That is Earth's first anomaly. Beneath our feet, starting just a few kilometers below the surface and extending thousands of kilometers into Earth's interior, something extraordinary is happening. The planet's insides are moving. Slowly, yes, at roughly the speed fingernails grow, but ceaselessly and with consequences that have shaped the entire history of life on Earth. This might seem unremarkable until you realize that among the 4 rocky planets of our solar system, Earth is the only one still doing this. Mercury, Venus, and Mars have all gone geologically quiet in different ways and for different reasons. But Earth alone maintains the active process known as plate tectonics. The planet's surface is not a single unbroken shell, but rather a mosaic of roughly 15 major rigid plates, each consisting of crust and upper mantle rock, fitted together like an enormous jigsaw puzzle and drifting across the planet's surface at rates of a few centimeters per year. Where plates collide, mountain ranges thrust upward, the Himalayas being the most dramatic current example, as the Indian plate crashes into the Eurasian plate. Where plates pull apart, new crust forms from upwelling magma along mid-ocean ridges, the longest mountain chain on Earth running along the floor of the Atlantic Ocean, where one plate dives beneath another in a process called subduction. Deep ocean trenches form and volcanic arcs ignite. The Pacific Northwest's Cascadia subduction zone, where the Juan de Fuca plate slides beneath the North American plate, is a prime example of this process and the source of the region's significant earthquake and volcanic hazard. Why is Earth alone in maintaining this mechanism? Consider Mars first. Mars has roughly half Earth's diameter and only about 1/10 its mass. Being smaller, it lost its internal heat to space far more quickly. Like a small cup of coffee cooling faster than a large pot. Its rocky shell, technically called the lithosphere, became too thick, too cold, and too rigid to crack into moving plates. Mars is essentially a one-plate planet now. Its interior too cool to drive the convective motions that would be necessary to break and move surface plates. Venus presents a more puzzling case. Nearly Earth's twin in size and mass, Venus almost certainly retains substantial internal heat. Yet it shows no evidence of active plate tectonics today. Research published in 2023 suggested that Venus may have had plate-like motions very early in its history, between roughly 4.5 and 3.5 billion years ago, but at some point the process shut down. The leading explanation involves water, or rather its absence. On Earth, water plays a decisive role in making plate tectonics work. It lowers the melting point of rocks, it reduces the viscosity of the asthenosphere, the partially molten layer beneath the rigid plates, allowing plates to slide more easily, and it lubricates subduction zones where one plate dives beneath another. Venus, with its surface temperature of approximately 470 degrees Celsius and atmospheric pressure 92 times that of Earth, lost whatever liquid water it may once have possessed billions of years ago. Without water to facilitate the process, plate tectonics ground to a halt. The consequences of having or lacking plate tectonics extend far beyond geology. This mechanism is arguably the single most important long-term climate control system Earth possesses, operating through what scientists call the carbon silicate cycle. Here is how it works. Carbon dioxide in the atmosphere dissolves in rainwater to form a weak acid called carbonic acid. This acid rain falls on exposed continental rocks and chemically weathers them, breaking down silicate minerals and releasing calcium and bicarbonate ions into solution. Rivers carry these dissolved minerals to the ocean, where marine organisms incorporate them into calcium carbonate shells. When these organisms die, their shells sink to the seafloor, locking carbon away in sedimentary layers. Over millions of years, the movement of tectonic plates carries these carbon-rich sediments into subduction zones, where they are dragged deep into Earth's mantle. Eventually, volcanic activity releases this stored carbon back into the atmosphere as carbon dioxide, completing the cycle. This feedback loop acts as a planetary thermostat. If the climate warms, chemical weathering accelerates because wet conditions dissolve rocks faster, pulling more carbon dioxide out of the atmosphere and cooling the planet back down. If the climate cools, weathering slows, carbon dioxide accumulates from ongoing volcanic emissions, and the greenhouse effect strengthens, warming the planet back up. This self-regulating mechanism has kept Earth's surface temperature within a range compatible with liquid water for billions of years despite the sun's luminosity increasing by roughly 30%. Over that time, Venus demonstrates what happens when this thermostat breaks. Without plate tectonics to recycle carbon, volcanic carbon dioxide simply accumulated in the atmosphere with nothing to remove it. The result is an atmosphere that is 96.5% carbon dioxide, producing a runaway greenhouse effect that maintains surface temperatures hot enough to melt lead. Earth and Venus started with similar sizes, similar compositions, similar distances from the sun. Yet one became a lush blue world teeming with life, while the other became a hellscape. The presence or absence of plate tectonics was the fork in the road. And here is what makes this truly anomalous. Scientists still cannot fully explain why Earth has maintained plate tectonics for over 4 billion years. It appears to require a precise combination of conditions, including the right amount of internal heat, the right water content in the mantle, the right planetary size, and the right interior composition. Remove any one ingredient, and the whole system might fail, leaving Earth as geologically dead as Mars, or as climatically doomed as Venus. The ground beneath us moves, recycling carbon, building continents, and regulating climate across billions of years. And this seemingly mundane fact is actually one of the most extraordinary things about our planet. Earth possesses an invisible shield that extends tens of thousands of kilometers into space, deflecting a relentless stream of charged particles that would otherwise strip away our atmosphere and irradiate the surface. This shield is the geomagnetic field, and its existence depends on conditions so specific that neither of our rocky planetary neighbors managed to maintain one. The magnetic field is generated deep within Earth's core through a mechanism called the geodynamo. Earth's core is a two-layered structure consisting of a solid inner core, roughly the size of the Moon, and composed primarily of iron and nickel, surrounded by a liquid outer core about 200 kilometers thick. The liquid iron in the outer core undergoes convection, rising and falling as heat escapes from the inner core outward, and this flowing electrically conductive fluid generates electric currents that in turn produce the magnetic field, much like a self-sustaining dynamo or generator. The resulting magnetosphere, the region of space dominated by Earth's magnetic field, forms an elongated bubble around the planet, compressed on the side facing the sun and stretched into a long tail on the opposite side. This magnetic bubble intercepts the solar wind, a continuous outflow of charged particles, primarily protons and electrons, streaming from the sun at speeds of 400 to 800 kilometers per second. Without the magnetosphere, these particles would slam directly into the upper atmosphere, gradually stripping away atmospheric molecules through a process called sputtering. Additionally, the magnetic field deflects high-energy cosmic rays from deep space that would otherwise bombard the surface, damaging DNA and making complex surface life extremely difficult. The reality of what happens when a planet loses its magnetic protection is not theoretical. Mars provides a stark demonstration. Mars once had a global magnetic field, as evidenced by strongly magnetized patches of ancient crust detected by orbiting spacecraft. However, roughly 4 billion years ago, Mars's dynamo shut down. The planet's smaller size meant its interior cooled more rapidly than Earth's, the liquid iron core eventually becoming too sluggish to sustain the convective motions necessary for field generation. Once the magnetic shield dropped, the solar wind began directly impacting the Martian atmosphere. Over hundreds of millions of years, this relentless bombardment stripped away the bulk of Mars's air. NASA's MAVEN spacecraft, orbiting Mars since 2014, has directly measured this ongoing atmospheric loss, detecting oxygen, carbon dioxide, and hydrogen atoms being ripped away by the solar wind at a rate of about 100 grams per second even today, when only a thin remnant atmosphere remains. Mars's atmospheric pressure is now just 0.6% of Earth's, far too low for liquid water to persist on the surface. In November 2025, NASA launched ESCAPADE, a mission consisting of 2 small spacecraft designed to orbit Mars simultaneously and map in unprecedented detail how the solar wind interacts with what remains of the Martian magnetic environment. By February 2026, the mission's scientific instruments were fully operational, providing new data on the mechanisms of atmospheric escape. One particularly striking finding from Mars research involves the counterintuitive role of weak residual magnetic fields. Mars still possesses localized patches of crustal magnetism, remnants of its ancient global field frozen into rocks. Rather than protecting the atmosphere in those regions, these weak, patchy fields may actually accelerate atmospheric loss. The mechanism works like this: solar wind pressure deforms the weak magnetic field lines, creating funnel-shaped structures that channel atmospheric ions outward into space rather than holding them in. Analysis suggests that atmospheric escape rates in regions with weak residual magnetism can be up to 6 times higher than in regions with no magnetic field at all. A shield that is too weak does not just fail to protect. It actively makes things worse by creating escape pathways that would not otherwise exist. This finding has profound implications for understanding planetary habitability and highlights just how critical it is that Earth's magnetic field is not merely present but robustly strong. The maintenance of Earth's dynamo, requires an exquisitely specific set of conditions. The outer core must remain liquid, which depends on composition and pressure being precisely right. The inner core must be slowly solidifying, because this crystallization process releases both latent heat and light elements like sulfur and oxygen that rise buoyantly through the outer core, providing the energy that drives convection. The inner core is currently growing at roughly 1 millimeter per year, an extraordinarily slow process that has been feeding the dynamo for hundreds of millions of years. But there is a deeper puzzle. The inner core is estimated to have begun crystallizing only between 500 million and 2 billion years ago. Yet geological evidence shows Earth has had a magnetic field for at least 3.5 billion years, possibly longer. What powered the dynamo before the inner core existed? In 2025, a joint research team from ETH Zurich and the Southern University of Science and Technology in China made a significant breakthrough on this question. Their sophisticated computer simulations demonstrated that a completely liquid core, with no solid inner core at all, could still generate a magnetic field through thermal convection alone, provided the heat flow from the core into the mantle was sufficient. This means Earth likely had magnetic protection from its very earliest days, shielded by a thermally driven dynamo long before the inner core began to form and provide the compositional convection that powers the modern field. Earth's magnetic shield is maintained by liquid iron flowing thousands of kilometers below our feet, powered by the gradual crystallization of the inner core and the precise thermal conditions of the deep interior. Too small a planet, and the interior cools and the dynamo dies, as happened on Mars. Too different an internal structure or composition, and the field never develops in the first place. The invisible magnetic bubble surrounding Earth is not a guaranteed feature of rocky planets. It is a remarkable and perhaps rare phenomenon that has protected our atmosphere and surface life for billions of years. The fourth anomaly takes us far from Earth itself, out to a distance of approximately 484 million miles from the Sun, where the solar system's largest planet orbits in a configuration that has profoundly influenced Earth's history. Jupiter is a colossus, containing 318 times Earth's mass and accounting for more than 70% of all planetary mass in the solar system combined. Its gravitational influence dominates the architecture of the entire planetary system, and the specific way it exerts that influence has been crucial for Earth. For decades, the prevailing view in astronomy was the Jupiter shield hypothesis, a straightforward idea that Jupiter's immense gravity acts as a cosmic bodyguard for Earth, deflecting or capturing comets and asteroids that would otherwise impact our planet. The dramatic collision of comet Shoemaker-Levy 9 with Jupiter in 1994, observed in real time by telescopes around the world, seemed to validate this idea perfectly. Here was Jupiter literally absorbing impacts that might otherwise threaten the inner solar system. The reality, as revealed by more sophisticated computer simulations in recent years, is considerably more nuanced. When researchers modeled solar systems with and without a Jupiter-like planet, they found that removing Jupiter did not significantly increase the rate of long-period comet impacts on Earth. The reason is that Jupiter plays a dual role. Yes, it deflects some incoming objects away from the inner solar system, but it also gravitationally perturbs objects in the outer solar system, redirecting some of them inward toward Earth that would never have threatened us otherwise. Jupiter is simultaneously a shield and a catapult, and these two effects roughly cancel each other out for long-period comets from the outer reaches of the solar system. However, Jupiter's gravitational influence has been decisive in another way. Between the orbits of Mars and Jupiter lies the asteroid belt, a region containing millions of rocky bodies ranging from dust-sized particles to the dwarf planet series at nearly 600 miles in diameter. Under normal circumstances, this material would likely have accumulated into a planet. Jupiter's gravity prevented that from happening, its gravitational perturbations stirring up the orbits of objects in this region so violently that they could never gently coalesce. The asteroid belt remains a zone of fragmented, colliding rubble rather than a coherent planet, directly because of Jupiter. And ironically, Jupiter's gravity periodically ejects asteroids from this belt, sending some of them on trajectories that cross Earth's orbit, Research published in 2024 presented evidence that the asteroid responsible for the mass extinction event 66 million years ago, the impact that wiped out the non-avian dinosaurs and roughly 75% of all species on Earth, originated from beyond Jupiter's orbit, having been gravitationally perturbed inward. So Jupiter both prevented a planet from forming in the asteroid belt and occasionally flings pieces of that belt toward us. The truly critical factor is not simply that Jupiter exists, but where and how it orbits. Jupiter sits at approximately 5.2 astronomical units from the Sun. 1 astronomical unit being the Earth-Sun distance of about 93 million miles. And it follows a nearly circular orbit with an eccentricity of only 0.049. This combination of distance and orbital shape is what makes Jupiter's influence net positive for Earth's long-term habitability. Observations of other star systems have revealed just how unusual this configuration is. Among the first exoplanets ever discovered were hot Jupiters, gas giant planets orbiting their host stars at distances far smaller than Mercury's orbit around our Sun, completing a full year in just a few days. These massive planets are believed to have formed far from their stars, as Jupiter did, and then migrated inward through the protoplanetary disk. A 2025 large-scale analysis of over 500 hot Jupiter systems examined their orbital characteristics and confirmed 2 primary migration mechanisms. High eccentricity migration, where gravitational interactions with other bodies stretch the planet's orbit until tidal forces from the star gradually circularize it at close range. And disk migration, where the planet spirals inward through gravitational interaction with the gas disk from which it formed. If our Jupiter had undergone either type of inward migration, the consequences for Earth would have been catastrophic. A Jupiter-mass planet plowing through the inner solar system would have gravitationally scattered the rocky planets, either ejecting them entirely from the solar system, sending them plunging into the Sun, or disrupting their orbits so severely that stable conditions for billions of years would be impossible. The fact that Jupiter formed where it did, remained where it did, and follows a nearly circular orbit is not the default outcome for giant planets. It appears to be a relatively uncommon arrangement, one that allowed the inner rocky planets to orbit unmolested for the billions of years needed for complex life to develop. Earth is called a water world, and from space the name seems apt, with approximately 71% of its surface covered by oceans that give the planet its distinctive blue appearance. But this poetic description conceals a crucial quantitative truth. Earth is not awash in water. By mass, water constitutes only about 0.02% of the entire planet. If you shrank Earth to the size of a basketball, the total water on its surface would not even amount to a perceptible film. The oceans appear vast to us because we live on the surface, but relative to the planet's bulk, they represent an astonishingly thin veneer. And this thinness is not a deficiency. It is precisely what makes Earth habitable. If Earth had substantially more water, say even a few times the current amount, the oceans would be deep enough to completely submerge all continental landmass. A world with no exposed continents would lack the carbon silicate weathering cycle described earlier, meaning no mechanism to remove excess carbon dioxide from the atmosphere and no long-term climate regulation. Furthermore, at extreme ocean depths, water undergoes a phase transition under pressure to form exotic high-pressure ices, not from cold, but from the sheer weight of water above. These pressure ices would form a layer between the liquid ocean and the rocky seafloor, cutting off the chemical exchange between seawater and mantle rock that supplies essential minerals like iron, phosphorus, and sulfur to the biosphere. Life in such a deep ocean would be starved of the chemical building blocks it needs. Some discovered exoplanets appear to be water worlds of exactly this type, with water comprising up to 30% of their total mass, 1,500 times Earth's water fraction. These planets sit within their star's habitable zone, where temperatures allow liquid water. Yet they may be fundamentally inhospitable to complex life precisely because they have too much water. Conversely, too little water creates different but equally severe problems. Oceans serve as enormous thermal buffers for Earth's climate. Water has an exceptionally high heat capacity, meaning it absorbs and releases thermal energy slowly compared to rock or soil. This property moderates temperature extremes between day and night, between summer and winter, and between equatorial and polar regions. Ocean currents redistribute heat from the tropics toward the poles, preventing equatorial regions from overheating and polar regions from becoming even more frigid. Remove most of the ocean and continental interiors would experience extreme temperature swings, scorching during the day and freezing at night, with far less of the planet's surface remaining within the temperature range where liquid water and complex chemistry can persist. The origin of Earth's water remains one of the most actively debated questions in planetary science. The traditional explanation held that Earth formed relatively dry from the hot inner region of the protoplanetary disk, and water was delivered later by impacts from water-rich asteroids and comets originating in the colder outer solar system. Support for this idea came from measurements showing that the deuterium-to-hydrogen ratio in certain types of asteroids, specifically carbonaceous chondrites, closely matches that of Earth's ocean water. However, in April 2025, a research team from Oxford University published findings that challenged this narrative. They analyzed enstatite chondrites, a rare class of meteorite whose overall chemical composition closely resembles that of Earth's bulk silicate mantle. Enstatite chondrites are thought to represent the type of material that dominated Earth's feeding zone during planetary formation, essentially the building blocks from which Earth was assembled. These meteorites are time capsules from 4.55 billion years ago, preserving the chemistry of the inner solar system's primordial material. The Oxford team's analysis revealed that this material contained far more hydrogen, the essential ingredient of water, than previously assumed. The hydrogen was locked within mineral structures and would have been released as water during the high-temperature processes of planetary formation and differentiation. This implies that Earth may have been born with much of its water already inside, incorporated into the planet's very fabric from the beginning rather than delivered later by external bombardment. The two hypotheses are not mutually exclusive. Earth's current water inventory could well represent a combination of indigenous water that was present from formation and exogenous water delivered by subsequent asteroid impacts. But regardless of the source, the end result is a quantity of water that falls within an extraordinarily narrow range, enough to cover most of the surface and provide thermal regulation, but not so much as to drown the continents and cut off geological cycling. Research from ETH Zurich published in 2025 further complicated the picture of water on exoplanets by demonstrating that sub-Neptune-type planets, often optimistically described as potential water worlds, may in fact be unable to maintain liquid water on their surfaces due to thick hydrogen-helium atmospheres creating extreme greenhouse conditions. The precise water budget that Earth possesses, not too much, not too little, enabling simultaneously a functioning carbon cycle, mineral delivery from the mantle, thermal climate regulation, and exposed continents for biological diversity, represents the fifth anomaly. The air you are breathing right now is approximately 21% oxygen, and every cell in your body depends on this gas to extract energy from food through aerobic respiration. But Earth's atmosphere was not always this way. In fact, the current composition represents the result of two radical rewrites of atmospheric chemistry, each involving global catastrophe, and the oxygen concentration has been maintained within a remarkably narrow band for hundreds of millions of years through feedback mechanisms that scientists are still working to fully understand. When Earth first formed 4.6 billion years ago, its atmosphere bore no resemblance to today's. The primary gases were carbon dioxide, water vapor, nitrogen, methane, and ammonia, with essentially no free oxygen. This was a reducing atmosphere, chemically the opposite of our current oxidizing one. Life first emerged in this oxygen-free world, and for hundreds of millions of years, all organisms were anaerobic, thriving in conditions that would be toxic to most modern life forms. The first great atmospheric rewrite began with the evolution of cyanobacteria, photosynthetic microorganisms that figured out how to use sunlight, water, and carbon dioxide to produce organic matter, releasing oxygen as a waste product. This is the same fundamental chemistry that plants use today, and cyanobacteria invented it roughly 2.9 billion years ago based on fossil and geochemical evidence. But between the appearance of oxygen-producing cyanobacteria and the actual accumulation of oxygen in the atmosphere, roughly 500 million years elapsed. This enormous delay, spanning an almost incomprehensible stretch of time, occurred because multiple oxygen sinks absorbed all the oxygen as fast as cyanobacteria could produce it. Dissolved iron in the oceans reacted with oxygen to form iron oxides that precipitated to the seafloor, creating the vast banded iron formations found in ancient rock sequences across places like Minnesota's Iron Range and Western Australia's Pilbara region. Volcanic gases and reduced minerals on land also consumed oxygen. Research published by a team at Okayama University in November 2025 identified another factor. High concentrations of dissolved nickel in early Earth's oceans may have suppressed cyanobacterial growth rates, limiting oxygen production at the source. Additionally, a February 2026 study from MIT revealed that other microorganisms had already evolved oxygen-consuming enzymes, actively removing oxygen from their environment. The early biosphere was locked in a tug-of-war between oxygen producers and oxygen consumers, and for hundreds of millions of years the consumers won. Eventually conditions shifted. Nickel concentrations declined as certain types of volcanic activity waned. Environmental changes favored explosive cyanobacterial proliferation. Oxygen production finally outstripped consumption, and atmospheric oxygen levels began to rise in what is called the Great Oxidation Event, approximately 2.4 billion years ago. But this triumph of oxygen-producing life triggered one of the most severe crises in Earth's history. The early atmosphere contained large amounts of methane, produced by methanogenic archaea, single-celled organisms that thrive in oxygen-free conditions. Methane is a greenhouse gas with a warming potential roughly 80 times that of carbon dioxide. Over a 20-year time frame, when oxygen flooded the atmosphere, it reacted with methane, destroying this powerful greenhouse gas and catastrophically weakening the blanket of warmth surrounding the planet. Global temperatures plummeted. Ice sheets advanced from the poles all the way to equatorial latitudes. Earth entered a snowball Earth state, its entire surface locked under ice approximately 2.3 to 2.2 billion years ago in what is called the Huronian glaciation. How did Earth escape this frozen prison? With the surface sealed under ice, rock weathering ceased entirely. But volcanoes continued erupting beneath and through the ice, pumping carbon dioxide into the atmosphere with no weathering process to remove it. Over perhaps 10 to 50 million years, carbon dioxide accumulated to levels hundreds of times higher than today, eventually generating enough greenhouse warming to melt the ice and restore liquid water to the surface. The planet recovered, but the experience was a near-death event for the entire biosphere. After this crisis, the atmosphere settled into its second form, one containing meaningful amounts of free oxygen. Though concentrations fluctuated considerably over the next 2 billion years before stabilizing at levels sufficient for complex multicellular life. The oxygen concentration we have today, approximately 21%, exists within a surprisingly narrow viable range. Below about 16%, fire cannot sustain combustion, which matters not for campfires but for the terrestrial carbon cycle that depends on periodic natural fires to recycle organic matter. Above approximately 25%, even damp vegetation becomes highly flammable, and widespread conflagrations would prevent forests from reaching maturity. Geological evidence from the past 350 million years shows that oxygen levels have remained broadly between 15 and 30%, with particularly tight regulation between 21 and 24% during the last 150 million years. The mechanisms maintaining this stability involve complex feedbacks between photosynthesis rates, organic carbon burial in sediments, fire frequency, and weathering rates. A self-regulating system that has kept atmospheric oxygen within the narrow window compatible with complex aerobic life for an almost inconceivably long time. The atmosphere was twice violently rewritten, each time through processes that could easily have sterilized the planet or locked it into a permanently uninhabitable state. That Earth threaded this needle, emerging from each crisis with conditions more favorable for complex life than before, constitutes the sixth anomaly. The seventh anomaly requires us to zoom out dramatically. from the scale of a single planet to the scale of an entire galaxy. The Milky Way is a barred spiral galaxy approximately 100,000 light-years in diameter, containing somewhere between 200 and 400 billion stars. Our solar system orbits the galactic center at a distance of roughly 26,000 light-years, placing us about halfway between the center and the visible edge of the galactic disk. This position is not random happenstance in terms of habitability, and it represents yet another improbable sweet spot among the conditions necessary for complex life to persist over billions of years. The concept of a galactic habitable zone, analogous to the circumstellar habitable zone where liquid water can exist on a planet's surface, defines the region of a galaxy where conditions permit long-term biological complexity. Too close to the galactic center, and several hazards intensify dramatically. The density of stars increases enormously, meaning close stellar encounters that could gravitationally disrupt the outer solar system, sending comets raining into the inner planets, become far more frequent. Supernova rates climb steeply with stellar density, and a supernova exploding within roughly 30 light-years of Earth could deliver enough gamma radiation and cosmic rays to destroy the ozone layer and irradiate the surface, potentially triggering mass extinction. The supermassive black hole at the galactic center, Sagittarius A star with a mass 4 million times that of the Sun, periodically becomes active, producing jets and radiation that would sterilize nearby planetary systems. Too far from the galactic center, and a different problem arises. The outer regions of the galaxy are metal-poor, meaning they contain lower abundances of elements heavier than hydrogen and helium. These heavy elements, which astronomers confusingly call metals regardless of their actual chemistry, include carbon, oxygen, silicon, iron, and all the other elements necessary to build rocky planets and complex organic molecules. They are produced inside stars and dispersed by supernovae, accumulating preferentially in the inner regions of galaxies where more generations of stars have lived and died. In the metal-poor outer galaxy, rocky planets may simply be unable to form in sufficient mass or with sufficient chemical complexity to support life. Earth's position threads between these extremes, in a region with enough heavy elements to build a rocky planet with a metallic core and complex surface chemistry, yet far enough from the dense, dangerous inner galaxy to avoid frequent sterilization events. But the solar system's galactic positioning involves additional subtlety beyond simple radial distance. The Milky Way's spiral arms, those luminous bands visible in photographs of other spiral galaxies, are regions of enhanced star formation and therefore elevated supernova rates. They are not fixed structures but rather density waves, patterns that rotate around the galactic center at a specific angular velocity called the pattern speed. Individual stars, including the Sun, orbit the galactic center at their own speeds determined by their distance from the center. At one particular radius, the orbital speed of stars matches the pattern speed of the spiral arms. This radius is called the corotation radius. A star at the corotation radius moves in lockstep with the spiral pattern, neither overtaking the arms nor falling behind them. Stars inside this radius orbit faster than the pattern and periodically pass through spiral arms from behind, while stars outside orbit slower and are periodically overtaken by the arms. The Sun appears to be located near the corotation radius of the Milky Way, meaning it crosses through spiral arms relatively infrequently compared to stars at other galactic distances. Each passage through a spiral arm subjects the solar system to elevated supernova risk, enhanced cosmic ray flux, and gravitational perturbations that could destabilize the Oort cloud, the vast reservoir of comets in the outer solar system. Minimizing these crossings by sitting near corotation provides a significant long-term safety advantage. A remarkable study published in December 2024 added another layer to this picture by presenting evidence that the Sun did not form at its current galactic radius. Rather, it appears to have been born significantly closer to the galactic center, at roughly 60% of its current distance, approximately 16,000 light-years out rather than the current 26,000, over its 4.6 billion-year lifetime. The Sun migrated outward through gravitational interactions with the galactic bar structure and evolving spiral arm pattern. The researchers analyzed how radiation exposure and comet influx rates would have changed along this migration path, proposing that habitability should be understood not as a static zone, but as a dynamic orbit through the galaxy. What they termed a habitable orbit concept. One final aspect of the solar system's galactic context deserves emphasis. The Sun is a single star. This might seem unremarkable until you consider that a substantial fraction of stars in the Milky Way, estimated between 50 and 75% depending on the survey, exist in binary or multiple star systems, gravitationally bound pairs or groups of stars orbiting their mutual center of mass. Planets can and do exist in binary systems, but maintaining a stable planetary orbit for billions of years becomes significantly more challenging when two stellar gravity wells are in play. Depending on the binary separation and orbital parameters, planets may be restricted to orbits very close to one star or very far from both. And even these can become unstable over geological timescales due to gravitational perturbations. The Sun being single means Earth's orbit has been subject only to the gentle, predictable gravitational influence of one star for 4.6 billion years, allowing the long-term orbital stability that complex life requires. The eighth and final anomaly is perhaps the most philosophically provocative because it concerns not a physical characteristic of Earth, but the timing of our existence within cosmic history. Earth is approximately 4.6 billion years old in a universe that is approximately 13.8 billion years old. The planet formed roughly one-third of the way through the universe's current age. An intelligent life, meaning humans capable of contemplating the cosmos, appeared only within the last few 100,000 years, representing the final 0.005% of Earth's existence. This timing is not arbitrary. It is constrained by factors that create a surprisingly narrow window for intelligent observers to exist. The central constraint is the Sun's evolving luminosity. Stars like the Sun grow gradually brighter over their lifetimes as hydrogen fusion in their cores produces helium, increasing the core's density and temperature, and therefore the rate of nuclear reactions. When the Sun formed 4.6 billion years ago, it was approximately 30% dimmer than it is today. This creates what is known as the faint young sun paradox with modern atmospheric composition. Early Earth should have been frozen solid. Yet geological evidence clearly shows liquid water existed on the surface within the first few 100 million years. The resolution, as discussed earlier, lies in the early atmosphere's dramatically different greenhouse gas composition, with much higher concentrations of carbon dioxide and methane compensating for the reduced solar input. The critical point for our purposes is that the Sun continues to brighten, and this trend will eventually render Earth uninhabitable. Current models estimate that within 1 to 2 billion years, solar luminosity will increase sufficiently to push Earth's surface temperature beyond the point where the oceans begin to evaporate. Water vapor is itself a potent greenhouse gas, so evaporation creates a positive feedback loop. More water vapor means more warming, which means more evaporation, which means more water vapor. Once this runaway process begins, it cannot be stopped. All surface water will eventually evaporate. The water vapor will rise into the upper atmosphere, where ultraviolet radiation splits it into hydrogen and oxygen, and the lightweight hydrogen will escape to space permanently. This is precisely what happened to Venus early in its history. Earth's oceans will be lost, and with them all surface life. This means Earth's window of habitability has a definite expiration date. Life on Earth has existed for at least 3.8 billion years, and it took that entire span. From the first simple cells to photosynthesizing cyanobacteria, to multicellular organisms, to the Cambrian explosion of animal life, to the colonization of land, to the rise of mammals, to the emergence of human intelligence, to produce beings capable of understanding and observing the universe. The process required roughly 3.8 billion years. The remaining habitable window is 1 to 2 billion years. These two timescales, the time needed to produce intelligence and the time remaining before habitability ends, are of the same order of magnitude. We exist in the overlap. If Earth had formed just a few 100 million years later in cosmic history, or if the evolutionary process had been even modestly slower, perhaps delayed by one additional mass extinction event or a slightly less favorable mutation rate, intelligence might never have arisen before the window closed. The fact that we appeared in time, not billions of years early with nothing interesting yet evolved, and not billions of years too late after the oceans boiled away, but right in the narrow overlap where both sufficient evolutionary time has elapsed and sufficient habitable time remains, is itself a statistical anomaly that demands explanation. These 8 anomalies, considered individually, are each notable but perhaps not extraordinary. Moons exist around many planets. Some planets presumably have active interiors. Some may have magnetic fields. Gas giants are common. Water is abundant in the universe. Atmospheric chemistry evolves on many worlds. Many stars occupy relatively safe galactic neighborhoods, and timing constraints apply to any system with a brightening star. But what makes Earth genuinely anomalous is not any single factor in isolation. It is the simultaneous convergence of all 8 on a single planet. Each condition is necessary, but not sufficient for complex life. Remove any one, whether the stabilizing moon, the active tectonics, the magnetic shield, Jupiter's benign configuration, the precise water budget, the atmospheric transformation that produced oxygen without permanently freezing or sterilizing the planet, the safe galactic position, or the temporal coincidence of intelligence arising during the habitable window, and the chain breaks. In probability theory, when multiple independent low-probability events must all occur simultaneously, the combined probability is the product of the individual probabilities. Even if each factor individually has a probability of, say, 1 in 10, 8 such factors multiplying together yield 1 in 100 million. And many of these factors likely have individual probabilities far lower than 1 in 10. Earth, by this reasoning, is a profound statistical outlier, a data point that lies far beyond the expected distribution, something that should not exist within a normal dataset. How should we interpret this extraordinary convergence? 3 philosophical positions present themselves. The first is simply to call it a miracle, to accept that Earth is a genuinely improbable fluke in a universe of mostly dead worlds, and to marvel at our fortune in existing at all. The second invokes the anthropic principle, or observation selection effect. The universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, orbited by trillions upon trillions of planets. The overwhelming majority of these planets are uninhabitable. But intelligent observers can only find themselves on planets where all necessary conditions happen to be met, simply because observers cannot exist anywhere else. From this perspective, our finding that Earth is anomalous is not surprising at all. It is a logical inevitability, given that we exist to make the observation. We are like a lottery winner marveling at the odds while forgetting that someone had to win, eventually given enough tickets sold. The third possibility is perhaps the most scientifically exciting, that we are wrong about the independence of these factors. If some yet undiscovered physical principle or set of causal connections links these conditions together. If having plate tectonics makes having the right amount of water more likely. If having a large moon is a natural consequence of the same formation process that produces an active core and magnetic field. If giant planets in circular distant orbits are the natural outcome for systems that also produce rocky planets in habitable zones, then Earth-like planets might be far more common than the naive probability calculation suggests. We simply have not yet identified the underlying mechanism that connects these apparently independent variables. Current science cannot definitively distinguish between these interpretations. We have a sample size of one habitable planet, which is the worst possible basis for statistical inference. The coming decades of exoplanet characterization, particularly with the James Webb Space Telescope and future missions designed to directly image and analyze the atmospheres of rocky planets, may begin to provide the data needed to assess how rare or common each of Earth's anomalous characteristics truly is among the broader population of planets in our galaxy. But one thing is certain without any philosophical ambiguity. You are reading these words. That fact alone is proof that all 8 anomalies converged on at least one planet in the observable universe. in a cosmos 13.8 billion years old. On a 4.6 billion year old rock orbiting an ordinary middle-aged star in the quiet suburbs of an unremarkable spiral galaxy. Atoms arrange themselves into patterns complex enough to contemplate their own improbability. Whether that makes Earth a miracle, an inevitable consequence of observation bias, or a natural outcome of physics we have yet to understand, it remains one of the most extraordinary facts we know. The ground beneath your feet is not ordinary ground. The air in your lungs is not ordinary air. The moment of cosmic time in which you exist is not an ordinary moment. Every aspect of your existence rests upon a tower of improbabilities, so staggering that the universe itself seems uncertain whether you should be here at all. And yet here you are, an anomaly contemplating anomalies. Proof that the impossible sometimes happens anyway.